Okay, today we'll be talking about support vector machines, which are one of the more popular machine learning algorithms out there. And support vector machines are one of those algorithms which will work reasonably well without having a lot of tuning required. Like, unlike neural networks, you don't have to really play with a lot of hyperparameters. And the default implementations or the default set of hyperparameters would generally be fairly good for support vector machines. And the base case of using support vector machines is for binary classification. Although this can be extended both to multi-class classification as well as regression settings, but SVM is by default the most suited to the case of binary classification. So in this sense, it appears that so linear regression is default suited for regression task, and we can modify that a little to do logistic regression, which becomes suitable for classification task. Similarly, support vector machines are default suited for classification task, but then you can do something on top of that, make use of some of the rules and make it useful for even the regression tasks. For today's lecture, we'll be focusing only on the classification aspects of support vector machines. The idea is really simple in support vector machines or SVMs. Let's say you have two set of features, feature 1 and feature 2, and I've made a scatter plot amongst these two, amongst the set of points, for all the set of points, and you can very clearly see that these 2 points seem to be separated, right? There seems to be a set of points blue here and a set of points belonging to the red class over here. The idea in support vector machines is to draw separating hyperplane. We'll come to the difference of what is a hyperplane in different dimensions, but for this particular case, since it's a two-dimensional input, a hyperplane is simply a line that you can draw and separate out the red class and the blue class. So that's first part of the intuition, and you would have expected this. I mean, this is fairly trivial to understand that such a classification makes sense, but then there are some more nuances to it. The main idea is to maximize something known as the margin. So you draw a separating hyperplane, which is shown in which I'm just highlighting right now, and you also draw something known as a margin. So margin is basically telling you the distance between the nearest set of points of opposing classes. In this particular case, the red and the blue, this red point and this blue point are lying on the margin. So that's essentially the idea, that you drew this classification in a sense that the margin is maximized. Now, I would request you to think for a minute why maximizing the margin makes sense. Assuming you paused and thought about it for a minute, maximizing the margin will lead to the least amount of confusion or chances of misclassification. So that's the reason you want to maximize the margin. And the points which lie on the margin are called the support vectors. Now, this is how the term support vector machine gets its name. And if you're wondering what is the support aspect of this and what is the vector, so each of these points you can think of as a vector in a some dimensional space. So think of these points as supporting the margin, or supporting the hyperplane and then the corresponding margin. So based on these, we are deciding, or we are establishing the margin. That's why these are known as support vectors, and we'll study a few properties about these support vectors and why, in essence, these are the only points that you need to save or store in order to learn an SVM classification. One important thing which I should say right away before I forget this: SVMs are extremely useful when you have very high dimensional data, and and in many cases, even if you have more features than dimensions, or sorry, more features than the number of samples, SVMs are likely to work better than many of the other algorithms. Let's now try and understand that what is the separation and what is this hyperplane that we can use to separate out points. To take the first example, we take a case of a 1D classification task. We have two classes of points, blue and red. And as you might see, since this data is only one dimensional, the separation between them, or how to categorize that something on one side is red class and something on the other side is blue class, can be decided just on the basis of a point, since the data is 1D. So the hyperplane in this particular case for an SVM classification would just be a single point. For a 2D case, which is what we've been seeing thus far, you require a line to separate these two classes. And if you take something which is three-dimensional or more, you require a high-dimensional plane or a hyperplane. So in this case, you see that these are three-dimensional points, and you're separating them out with this hyperplane. So that's essentially how we can interpret how to use, how to understand different hyperplanes, and how the dimensionality of the input features changes the exact specification of the hyperplane that we're using, but the techniques developed remain general. Okay, so I have a question for you. Which hyperplane should you be choosing? Do you choose this hyperplane, which, as you might see, is separating out the data reasonably well? I mean, so you can see that the blue and the red are on the opposite side of the hyperplane, so this hyperplane works for us. What about this hyperplane? Any disadvantage of this hyperplane? So as you might have seen, this hyperplane is sort of getting into the risky zone, because there are some blue points which are very close to this hyperplane, and this particular hyperplane which you see now is probably the best suited. Any thoughts why? Yes, because it is going to now be maximizing the margin. So if you draw hyperplane in this line as your hyperplane, and you draw the margin, you'll see that the margin is fairly large. So this distance will be the margin. But if you were to draw somewhat of a different hyperplane, you'll have a lower margin, which is always risky. So which means that you have higher chances of misclassification. Now we've discussed what is a hyperplane. We've also seen that we want specific types of hyperplane. We'll of course get into the nitty-gritties and the in-depth mathematics of hyperplane and the separating hyperplane in a minute. Before that, we must quickly understand that how do we represent a hyperplane via an equation, via a vector equation. So let's try to define a hyperplane. This is the hyperplane that I'm trying to now define, and I've drawn an origin in this space. So think of it as any high dimensional d-dimensional space. So what we need to define this hyperplane is, we want to define it for any point P lying on this plane, right? So that's the equation. If you can describe the equation for any point P, you have described the entire plane. So you say that P is any point on the plane. P naught is a given point on the plane. So think of P naught as 1 comma 3 or 4 comma 5 comma 6, something on that line. So it's anything which is given to you, so you know that this point indeed lies on the plane. Capital P is the any general point on this plane, and P naught is a specific known point on this plane, on this hyperplane. Now we start from the origin, and we then draw vectors to the point P and P naught. The vector to the point P is called the x vector, and the vector to the point P naught is called the x naught vector. So if you see, I'm using wherever we so because there is point P naught, the vector to that is called x naught, right? And what do you now think about the vector P naught or P naught P? How can you write that? Before that, since we've already mentioned that P lies on the plane and P naught, so P is the equation of any point on the plane and P naught lies on the plane. In essence, we're writing that both P and P naught are going to be lying on the plane, right? And now we've defined the vectors x and x naught to be the vectors to P and P naught. Sorry, I think I forgot one particular slide. Yes. Another thing which you require to define the equation of a hyperplane is a perpendicular vector to the plane at the given point, right? So in essence, to define a plane, you just require a point on the plane and a normal or a perpendicular vector to the plane at that point, which is now represented by the vector w, right? And x and x naught are the vectors to the point P and P naught. We can write the vector P naught as x minus x naught, right? And what can you say about the vector P naught? Can you say that it lies on the plane? Yes, you can say that. And we've already seen that W vector is perpendicular to the plane at P naught. So what kind of relationship exists between x minus x naught vector, which is the P naught vector, and W vector? The relationship is fairly simple. Since W is perpendicular to the vector at perpendicular to the plane at P naught, so thus W is also perpendicular to the vector x minus x naught, which lies on the plane. Thus we can write W dot, the dot product between W and x minus x naught, to be 0, or we can write W dot x minus W x naught vector equal to 0. Now x naught is a known quantity, right? So we just rewrite this entire expression to create an equation of an hyperplane, which is W dot x plus b equal to 0. Now you can of course vary the dimensionality of x to confirm this particular this equation of a hyperplane. You could just keep it to one dimensional and then you'll get wx plus b equal to 0. You can keep it to two dimensional, w1 x1 plus w2 x2 plus b equal to 0. So you can keep varying that and you can get a sense of the equation of the hyperplane. The next thing which we require to mathematically develop an SVM is the distance between two hyperplanes. I'll quickly go back a few slides and explain why this particular thing is required. So if we go back to this slide, here the separating hyperplane is a hyperplane. This particular line which you see here is also in high dimensional space a hyperplane, and so is this particular line, right? And we said that we want to maximize the margin, right? So in some sense you want to maximize the distance between these two dotted lines, or these two hyperplanes. So we need some mechanism of finding the distance between two hyperplanes. First, to develop that theory or develop that result, we have firstly described what is the equation of a hyperplane. That is given in terms of a point on that plane and a perpendicular to that point, or perpendicular to that plane passing through that point. And the equation of a hyperplane we then get is w dot x plus b equal to 0. B is a scalar, right? So coming back to now finding the distance between parallel hyperplanes. So I'm also going to call them parallel hyperplanes, as you would expected. These planes are indeed parallel. So if you go back, the idea behind this margin is that this particular line, so basically the separating hyperplane is is in between, exactly midway between this line and this line. So that's why these are going to be parallel hyperplanes, and the separating hyperplane is going to be just the just halfway distance from these two. So thus we're dealing with parallel hyperplanes, and just for simplicity we can write these two hyperplanes as wx plus b1 equal to 0 and wx plus b2 equal to 0, where you can, for now let's not worry about b1 b2 or the sign of b1 b2. And as before, we create an origin just to put up a reference system, and we say that any point lying on the plane wx plus b1. Let's just call it the x1 vector, and let's call this point on the second hyperplane, which is directly above this particular, or if you draw a perpendicular from this point lying on plane 1 and you intersect it with plane 2, the point that you get is the x2 vector, right? So naturally now you know that there is an x1 vector and then there is an x2 vector, and we of course know that the perpendicular vector to both of these hyperplanes is the w vector, right? But what we don't know is how many times the magnitude of that particular vector is this particular hyperplane. So if we start from this hyperplane, we know that if we go in the direction of the w vector, we'll reach the other hyperplane. But how many times? So we just call that scalar as t. So this distance is t times the w vector. Can you now look at all of these numbers on this slide and tell me what is the distance between these two hyperplanes? So I'm assuming you stopped the video and you're working through the solution and you found out a solution. I'll go through the solution now. So we have already written that the equation of the two planes is wx plus b1 equal to 0 and wx plus b2 equal to 0, and we have already said that x2 equal to x1 plus tw. So you can always go back and just verify. X2 vector is the vector sum of x1 and tw, right? And you can also write the distance between these two planes as the magnitude of tw, right? And where t is anyway a scalar, so you can take t out and just take the magnitude of it, multiply it with the magnitude of w, and that is the distance between these two hyperplanes. So that's essentially what we're trying to now calculate. So the distance between these two hyperplanes is the magnitude of tw, and since t is a scalar but it can be negative, so you take the absolute of t and you multiply that with the magnitude of w vector. That's the distance between these two hyperplanes, and we can rewrite the above set of equations in the following way. So we take this equation wx plus b2 equal to 0, and we know that the point x2 lies on this plane, right? So we can write that wx2 plus b2 equal to 0, but we also know that x2 is x1 plus t times the w vector. So we just replace x2 with x1 plus t times the w vector, and we can thus write w dot x1 plus tw vector plus the scalar b2 equal to 0, right? And we can, let's just expand this out, and then we'll get that w times x1 vector plus t scalar times w dot w, which is just the square of the magnitude of, or the square of the length of the vector w, plus b2 equal to 0. But we already have something in the terms of wx1 plus b1 equal to 0. We already know that. But this particular equation has no reference to b1, so we can just add b1 and subtract b1, right? So we add b1, we subtract b1, and we already know that wx1 plus b1 is 0, right? Since x1 lies on this particular hyperplane, so we can then rewrite this, and all we're left with is minus b1 here plus b2 here and tw, the magnitude square times t. So thus we can write t equal to, you take b1 there and b2 there, so the signs will get b1 minus b2 divided by the magnitude of w squared. But d, the distance between these two hyperplanes, was t times the magnitude of w. So we can write d equal to t times the magnitude of w equal to, so t is replaced by b1 minus b2 divided by the square of the magnitude of w. Thus you're left with d, distance between these two hyperplanes, is b1 minus b2 divided by the magnitude of w. This is an important derivation. I would request you to work this out on your own to get more confidence into this particular set of this particular like type of calculations. Let's now proceed further and understand the SVM formulation. And I'll just use a simple 2D case to illustrate this formulation. I'm going to be calling the blue class as -1 for the purposes of this example, and the red class as the +1 class. So this is where you'll also see, this is the reason why you'll see that many machine learning classifiers use the negative class as -1 and the positive as +1. In some specific implementation of some algorithms, you would have seen that the two classes are encoded as 0 or 1, right, in the binary sense. But -1 and 1 do lend its importance here. And I would not answer this question, but I would hope that you're able to answer this yourself at the end of this lecture. Okay, so let's just write the equation of these hyperplanes as wx plus b equal to -1 and wx plus b equal to +1. So we have written these in one specific format just to aid our calculations, right? And once you've written these equation of these hyperplanes in this particular fashion, by the way, w and b are the unknowns here, right? So this is what you're trying to now estimate in the learning phase of this algorithm. So you can calculate the margin between these two hyperplanes as follows. So the margin, if you remember the formula for margin, is b1 minus b2 divided by the magnitude of w, right? So b1 minus b2 we can write as, so this particular hyperplane is wx plus b plus 1 equal to 0, and this one is wx plus b minus 1 equal to 0. The margin will turn out to be 2 divided by the magnitude of w, right? So this is the margin. That's the first part of the formulation, and we've been discussing thus far that our goal is to maximize this margin, right? So you can maximize this margin, which means you want to maximize 2 over the magnitude of w. So you want to maximize 2 over the magnitude of w, which can also be rewritten as minimize the magnitude of w, which can be rewritten as minimize the square of the magnitude of w, right? But there is an important set of constraints that you want to identify. Let's say that if there were no constraints and you just want to maximize the margin, so in that case you'll see that you might have the wx plus b equal to 1 as something over here, and wx plus b minus 1 could be somewhere over here, or you could keep extending those in the opposite directions. That way you would be maximizing the margin. But does that help you in any sense? No, right? Because your main aim is not to maximize the margin, your main aim is to classify the points correctly. So thus this is the objective, that you want to minimize w, but there are constraints, and the constraints come in the form of you want to correctly classify or label the points. You want to correctly classify all of these points. A big assumption at this point of time that we're making, and let's be very clear about this. This is the case where the data is trivially linearly separable. So something like the case you're seeing here. Do not think about using complicated non-trivial or non-linearly separable case at this point of time. We'll eventually get to that in advanced SVM lectures. But for now, the data is, you just assume it to be linearly separable, and it's as trivial as the case that you're seeing over here. Right. So what does it mean to correctly label the points? Right. So what do you think would be the value of wx plus b for some points over here? Would it be 1? Would it be greater than 1? Would it be less than 1? Would it be 0? What do you think? So this particular line you think as is wx plus b equal to 0. So you see that wx plus b is increasing in this particular direction, right? Similarly, wx plus b is decreasing in this particular direction, and you would expect wx plus b for all of these points to be strictly greater than 1, because you'll say that wx plus b equal to 1 or minus 1, strictly for the support vectors, and these points are not support vectors, as in they are not supporting the margins, they are further away from the margin, right? So let's look at the red class or the positive class for now. What we're saying is that for the positive class, wx plus b equal to is greater than 1, right? And if we look at all the red points, we can say that wx plus b is greater than equal to 1, right? This is for the plus 1 class. For the minus 1 class, we say that wx plus b is less than equal to minus 1, right? So plus 1 class, we say wx plus b greater than equal to 1. Minus 1 class, we say wx plus b less than equal to minus 1. Can we combine these two cases in a smart way to write a single equation? That's a brain teaser for you. I'm assuming you stopped the video, thought about this. So we have said that y1 equal to minus 1, yi equal to, if yi equal to minus 1, then wx I, sorry, if for the negative class wx plus b is less than equal to minus 1, and for the positive class wx plus b is less than equal to 1. In general, this should be, also have an index I. So this means that if the ith point, so wi times wi is a scalar, wx plus b is greater than equal to 1. You basically multiplied wi with wx plus b, and since if it is negative 1, then this sign changes and you still get greater than equal to 1. So in one particular equation, in only a single line, you can represent both these types of points, right? So now we have written down the complete formulation of the trivial SVM in the case of linearly separable data. That the objective is to minimize w or w squared, the magnitude of w, such that all the points are correctly classified or labeled, which means yi times wxi plus b is greater than equal to 1, right? Just to rewrite this in a clearer way, minimize, and if you might be wondering what is this half coming from, so this is generally a synthetically or cosmetically introduced term. It's very useful in this, it's like conventionally used whenever you have w squared time of or theta squared time of type of term, so that once you differentiate this term, this to the power of 2 and the fraction half will get cancelled, not cancelled in that sense, you'll get a 1 when you multiply these. So that's the idea, that's one idea behind using half w squared, otherwise it does not really matter, right? So this is the objective, and we have these set of constraints. But an important quick question to verify your understanding: what is the magnitude of w, right? So we, as we've been doing thus far, think of w as a vector rd or rn in this case. So it's spanning multiple rows but a single column, and the magnitude of w you can think of as square root of w1 squared plus w2 squared till dot dot wn squared, which you can think of as the square root of w transpose w, right? Because you can write w transpose as the vector consisting of one row and n columns multiplied by the vector containing n rows and one column, and if you do this multiplication, take the square root, you get a scalar. That particular quantity is the magnitude of w. So let's take one trivial example in one dimensional space and solidify our understanding of what w, b, etc. would mean. And we'll also, through this exercise, geometrically understand and interpret SVMs better. This will also help us better revise constraint optimization that we'd been studying earlier, a long time back in the first part of the semester. So we have, I'm showing you 4 points, 2 red points and 2 blue points, and I've darkened the support vectors. So it seems obvious that for this example, the separating hyperplane would be a single point, and these 2 points, the red and the blue point, to the proximity of the separating hyperplane would be the support vectors, right? So let's assume that these 4 points are corresponding to x1. We have y1, x2, y1, and x minus 1 is y minus 1, and x minus 2 is y minus 1. So This is x1 y1 x2 y1 x minus 1 y minus 1 and x minus 2 y1. Right? So you have 4 points and the support vectors are x1 and x minus 1, right? And we know that the separating hyperplane is of the form wx plus b equal to 0. Our objective here is to learn what is w and b, right? Since x is now just a single dimensional, uh, x has only one feature, so we can essentially just write this separating hyperplane in this scalar form simply as wx plus b equal to 0, getting rid of the vectorial notation here, since x is in essence a scalar, right? And we know that there are these inequalities or these constraints which we must follow, right? Which is yi times wx plus b is greater than equal to 1, right? So let's now write these constraints for each of these 4 points. We have 4 points, right? Let's write the constraint for each of these 4 points and let's draw them on a 2D plane and see what we can learn from it. So corresponding to the first point 1 1, since y is 1, we write this particular constraint equation as y equal to 1 times w into x is 1 plus b is greater than equal to 1. So we write 1 times w plus b is greater than equal to 1. For the second point we write 1 times 2w plus b greater than equal to 1. For the third we have y equal to minus 1. So minus 1 times minus 1 into w plus b greater than equal to 1. And for the fourth point we write minus 1 times minus 2 into w plus b greater than equal to 1. So now you have 4 inequalities which we'll now plot on a 2D space, where we'll choose one of the dimensions as w, the other dimensions or the other coordinate as b, right? And then if you remember, the goal was to minimize w or the magnitude of w. So once we draw this inequalities, we'll try and geometrically interpret and reason about w. Okay, the first inequality is that w plus b greater than equal to 1, right? So the first thing I'm going to do is to just draw w plus b equal to 1. So w is now the x-axis and b is drawn on the y-axis, and w plus b is going to pass through the points 0 1 and 1 0, and I'm just drawing w plus b equal to 1. Now which side of this line is the inequality true? For that you'll need to see. So w plus b greater than equal to 1. So there are multiple ways in which you can do. One is you see where does the origin lie. You put 0 is 0. Is 0 plus 0 greater than equal to 1? No. Which means that the inequality lies on this side, right? Or you can in general see that if you see anything on this side of the inequality or the side of the line, the w plus b value is going to be greater than equal to 1, right? The second inequality was 2w plus b greater than equal to 1, and the way I suggest to write this is to write w by half plus b by 1 equal to 1. You draw a line for that and then you see which side of the inequality you need to be on. So I draw w by half, which means that the intercept on the w axis is half and the intercept on the y axis is 1, and I write this is basically 2w plus b equal to 1 line. And again I see in which direction I should be drawing this inequality. Since origin is on the wrong side of this inequality, basically this inequality is in this direction. So this is the feasible region for this is the region of interest for this particular inequality, right? So now we have drawn two inequalities and you can see that they're both going to impose something useful for the overall objective. At least it seems at this point of time, but we'll confirm that later. The third one was, go back, third one was w minus w plus b greater than equal to 1. So what I've plotted is w minus b equal to 1, w minus b equal to 1, and then Once you plotted w minus b equal to 1, then you again look at the direction in which this inequality will be satisfied, right? And that particular direction turns out to be this downward direction, right? And I do the same thing for the fourth inequality or constraint, which is 2w plus b, 2w plus, sorry, this is 2w minus b greater than equal to 1, and the earlier one was w minus b greater than equal to 1, right? So 2w plus 2w minus b greater than equal to 1. Sorry, this should have been 2w minus b greater than equal to 1. I think I plotted it correctly, but anyway, this is not important. This particular, we'll see that this particular constraint will not be important. Now let's look at all the set of constraints and let us understand that what will be our solution space. So you see that let's look carefully. So does this seem to be the region of interest where all of the inequalities hold, right? And I've just highlighted that this particular seems to be the most restrictive set of constraints, right? Because any point which is here will also be satisfied by this, and by this, so on and so forth. So, and on the opposite direction also we see this. So this red region which I have highlighted, not fully but partially I have highlighted, is the region where all the inequalities will hold true. And in this region we are trying to minimize w, right? Which is now a trivial exercise to do that. If you you look at where w minus b equal to 1 and w plus b equal to 1 intersect, that is on w equal to 1 and b equal to 0, right? So that becomes your point where w is minimized and all the constraints are also satisfied. So thus w equal to 1, b equal to 0 is your solution to this particular classification problem or this particular SVM. And if we just go ahead with this, substituting these values of w and b, we basically now writing wx plus b equal to 0 is the equation of the hyperplane of interest. Since w is 1, b is 0, we are essentially writing 1 times x plus b equal to 0, which means x equal to 0, which if we go back is exactly a separating hyperplane as we would have expected, right? So let's also look at another interesting thing. So which of the constraints are the binding constraints, or the constraints which necessarily play a part in the solution? If we zoom in, so it's constraint number 1 and constraint number 3. So if you see constraint number 4 is over here, it does not actively sort of change anything in the solution. So does constraint number 2 does not change anything in the solution. And if we go back and see, so this particular dark red point is the point number 1, the light red point is point number 2, the blue point is the point number 3, and the light or the hollow blue point is point number 4. As you would expected, the point 1 and point 3, which are closer to the separating hyperplane, right, are indeed the points of the margin, and they are indeed the support vectors. And only the constraints which are enforced by, or the constraints which map to the support vectors, they are the only binding constraints in this optimization, or they are the only important constraints in this optimization. This particular fact is important to know, especially because we'll be looking at solving the dual form of this solution or dual form of this problem as we've done earlier. So when we introduced the Lagrangian multipliers in the first half of the course, when we were discussing about constraint optimization. So in general, we have seen that we have seen the primal formulation, which is a quadratic program. So quadratic program is the form where you're trying to minimize a quadratic function of x given some linear inequalities or some linear function of x. For example, if one simple form of a quadratic program could be you're trying to minimize half times the magnitude of x squared given x1 plus x2 is greater than equal to 1, right? So it's you're trying to minimize, which is something quadratic in x, such that the constraints are linear in x. And we have already done this to some extent earlier, so I'll not go into the details. But if you remember, we had earlier been trying to solve this using the dual formulation or introducing Lagrangian multipliers. For the purposes of SVM, the dual formulation is extremely useful, and we'll hopefully understand this in the next particular lecture when I discuss this in more detail. For now, we just look at the formulation. I'll not discuss all of the advantages of the dual formalism for SVMs. Okay, this is an really important topic in SVM, so I would request you to pay a lot of attention to this. We'll be converting the primal objective, the primal quadratic program, which is this one: minimize half w squared or half times the magnitude of w squared, such that yi times wxi plus b greater than equal to 1 for all the i's. So this is correctly classifying all the points. We can convert this to a dual form, or the form where we are introducing Lagrangian multipliers. So if you remember, the Lagrangian function is now a function of the original variables w and b plus some alpha variables that we're introducing here. Since we don't have equalities, we'll be introducing the variables only for each of these inequalities. Assuming n points, we'll have n inequalities, which means we'll introduce n new variables, alpha 1 through alpha n, and we'll rewrite this in the form of half times w, the magnitude of w squared, which you can also write this assuming w is a d-dimensional vector, as the summation of w, the individual ith component of w, squared, summed over all the d dimensions. This is basically this expression, minus for each of the inequality, you first write it in the standard form. So which is yi times wxi plus b minus 1 is greater than equal to 0, and then you rewrite that as minus yi times wx plus b minus 1 is less than equal to 0, right? And if you multiply in alpha I corresponding to each of the ith constraint, where each of the alpha is greater than equal to 0, so you can then get this dual form, which is half times this expression minus summation over the capital N examples. Each example poses a constraint times alpha I times this expression yi wx plus b minus 1, and this is for all alpha I which is greater than equal to 0, right? So an important thing to note here is that the primal is a minimization over the magnitude of w. The dual is a maximization of over this L. So that's the relationship between primal and dual. In the primal, the quantity which is the objective is being minimized. In the dual, the new objective is being maximized. And as we had done before, the way we solve for the constraint optimization problem is then to differentiate with respect to the different variables of interest. So we can differentiate the Lagrangian function with respect to b first, and the first term does not have any element of b. The second term has alpha I yi b as the term containing b. Once you differentiate that with respect to b and sum it over n, you will basically get that summation over all the n examples of alpha I yi is 0, right? Since alpha I yi b summation differentiated with respect to b is 0, thus you get summation I equal to 1 to capital N, should be capital N here if we have introduced capital N over here, alpha I yi equal to 0. So that's the first equation that you get. Next, you can differentiate with respect to this Lagrangian function with respect to w set to 0, right? Let's see which of the terms contain W. The first term contains W and the second term also contains a W. So if you differentiate W, the magnitude of W with respect to W, or W transpose W divided by 2, if you differentiate that with respect to W, you'll just get W. And for the second term, you had alpha I yi W times W dot xi plus B minus 1 is you differentiate this with term with respect to W. So notice that alpha, yi, B are all scalars, W and X are the only vectors, right? And if you differentiate this with respect to the vector W, you will get summation I equal to 1 to n, alpha I, yi, xi is a vector equal to 0, right? So now you get some equation which is W minus something equal to 0. We can use that to calculate what is W. So now the W vector can be written in form of the uh, the Lagrangian coefficient for the ith constraint, ith example alpha I times yi xi. Now yi xi already known to you. Alpha I is what you want to calculate. Once you've done that, you can easily calculate W, and that's how you be essentially be able to solve or do the learning in the SVM, right? Now what we'll do is to go back to this original equation and substitute the value of W that we've just learned. So we can write W equal to summation over all the n examples of alpha I, yi, xi, right? Substituting the value of W in this particular equation. So essentially we'll get half of Wi squared over I equal to 1 to D. I'll basically substitute in the next iteration, and I'm going to break this whole expression down. So the first term is alpha I yi w xi. Let me just write it in this way. The second term is alpha I yi b, right? But we already know that the summation alpha I yi b is 0. Since summation alpha I yi is 0, therefore this term will become 0, and then there is this term of uh, alpha I, summation alpha I. Let's see, where is this term coming from? Have I missed a bracket over here? Yeah, I think I've missed a bracket over here. So this is, should be alpha I times yi wx plus b minus 1 the whole bracket. There should be a bracket over here, therefore plus the last term here is plus summation alpha I goes from 1 to capital N, right? So in this particular equation, I've just rewritten the alpha I term over here. I've expanded W, right? Now this needs to be done very carefully, because W is summation I equal to 1 to n alpha I yi xi, but this is essentially the magnitude of W squared, right? So which can be written as just as W dot W, right? So I'm writing that as a double summation, or a summation, to separate summations in some sense. So first is a summation carried out over the variable I. So you just write this particular equation in terms of variable I, and then you again write it in terms of a variable j, right? And you can again write minus alpha I yi w xi. You can replace W with alpha I yi xi, or just do it with j, since we are already using I over here, right? So I've just substituted W as equal to alpha j yj xj summation over j equal to 1 to n, and finally this thing has a dot product with xi, right? So I've essentially written this thing down. Now if you notice these expressions, let's just first take out all the scalars over here. So it's a summation over I and j, and you have alpha I, alpha j, yi, yj, and the vector left is xi, xj, and this entire thing is divided by 2. If you look at this expression, again summation over I and j, alpha I, alpha j, yi, yj, both of them are scalar. All of these are scalars. times xj dot xi or xi dot xj, doesn't matter given that these are just the dot product of two vectors, right? So essentially this thing is the half of this thing, right? And if we just rewrite the entire expression, we can essentially write that L as a function of alpha is equal to summation I equal to 1 to capital N of alpha I minus half summation I equal to 1 to n summation j equal to 1 to n alpha I alpha j yi yj xi dot xj. So don't worry if this double summation looks a little complicated. Very soon we'll do an example, and I think this particular kind of expression will become much clearer then. Just to summarize what we're trying to do here in terms of the mathematical formulation and what is the overall objective. So we're trying to minimize w, the magnitude of w squared in the primal form subject to the constraints. In the dual formulation, by introducing the Lagrangian variables, we maximize the dual objective, which is L of alpha, such that summation I equal to 1 to n alpha I yi equal to 0, right? So we obtain this by differentiating with respect to b, if you remember, right? So once we've done this and we have already geometrically interpreted SVMs, so and we already know a little bit about constraint optimization, right? In constraint optimization also we said that only those multipliers or only those coefficients corresponding to the inequalities which participate in this solution will be non-zero, else all of the coefficients will be zero if a particular inequality does not actively take part in the solution. So that's exactly what will also happen for the case of SVMs, because it's at the end of the day it's also constraint optimization that we're trying to solve. So we also know that as per the KKT conditions and the specific condition of slackness, we know that alpha I times yi w dot xi plus b minus 1 equal to 0, right? We know this. So the question is that what is the alpha I for support vector points, right? And as I was discussing before, so for the support vector points, the constraints are binding in nature. Just to revise this example, the support vector points corresponding to point 1 and point 3, those constraints are binding in nature, and corresponding to those, the multiplier for those constraints will be not 0, the multiplier for all of the other constraints will be 0, right? And to understand this again from a different sense, for the support vector points we already know that yi times w dot x plus b equal to 1, right? So this thing is already 0, which means that this thing will be non-zero, whereas for the case of the non-support vector points, yi times wx plus b minus 1 will be non-zero. Thus, since this entire thing has to be 0, this alpha I will be 0, right? So that's an important thing to remember. This is again something which will turn out to be an advantage for the dual formulation, that we'll need to look through a really small set of points while making predictions. So the important takeaway from this point is, for all the support vector points, alpha I is non-zero, and for all the non-support vector points, alpha I will be 0. Let's now try to redo the example which we had done earlier, but in the dual formulation, right? So we had these 4 points: x equal to 1, y equal to 1, x equal to 2, y equal to 1, x equal to minus 1, y equal to minus 1, and x equal to minus 2, y equal to minus 1, right? So this was a data set. Now I'm going to be writing the dual objective directly. Since there are 4 points, so there's 4 constraints and thus 4 alpha i's, right? So if you remember the formulation for L of alpha or the dual objective, it was first summation over alpha I. For us, I goes from 1 to 4, minus half times summation I equal to 1 to 4 summation j equal to 1 to 4 alpha I alpha j yi yj xi dot xj, right? And each of these alpha i's are greater than equal to 0. This is as per the definition and as per the discussion we've been having on constraint optimization. If some of these things do not appear to be clear, I would highly urge you to go back and revisit the constraint optimization lectures to understand why we made some of these assumptions. We already know that summation alpha yi equal to 0. This we got when we differentiated the Lagrangian objective with respect to b, set it to 0. And we also know that alpha I times yi times wxi plus b minus 1 equal to 0. We know that only for the support vectors the alpha i's are non-zero. For all the other non-support vectors alpha i's are 0, right? So we already know all of that background. We can then write this as, assume that alpha 1, alpha 2, alpha 3, alpha 4 are the 4 multipliers. We can write the objective as alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 minus half. So this is where I'm saying that if the double summation wasn't clear, if you look at this slide, it should hopefully be clear. So you double summation in this case would end up with 16 terms of the type alpha 1, alpha 3, alpha 1, alpha 2, alpha 1, alpha 3, alpha 1, alpha 4, alpha 2, alpha 1, alpha 2, alpha 2, alpha 2, alpha 3, alpha 2, alpha 4, and so on and so forth. So that's 16 terms, and correspondingly you'll have the yi, yj, xi, xj, right? So you could use a quadratic program solver and get a solution to this. But since this is a trivial example and we already know what the support vectors will be just by looking at the geometrical just by looking at the image of this problem, we already know that only the first point and the third point will be serving as the support vectors. So only these 2 points will have non-zero alpha i's, whereas the two extremities x equal to 2 and x equal to minus 2 will not have will have constraints which are not binding, and thus correspondingly their alpha i's will be 0, right? And since this problem is highly symmetrical in nature, I'll say that let's just keep alpha 1 equal to alpha 3 equal to some alpha, and we already know that x alpha 2 equal to alpha 4 equal to 0, right? So alpha 1 and alpha 3 will be symmetrically equal. So if we just rewrite this entire expression, we can write this as summation of alpha I will be just 2 alpha and minus half summation over I and summation over j of alpha I, alpha j, yi, yj, xi dot xj can be written as minus half times, you'll be only looking at the terms where either alpha 1 alpha, you'll be basically looking at 4 terms. So the first term is alpha 1 alpha 3 y1 is equal to 1, y3 equal to minus 1, x1 equal to 1, x3 equal to minus 1 plus alpha 3 times alpha 1 y3 into y1 into x3 into x1. So these should ideally be dot product, but in this case we're dealing with scalars, plus alpha 1 times alpha 1 y1 y1 x1 x1 plus alpha 3 into alpha 3 into y3 into y3 into x3 into x3, right? And if we just expand this out, this is 2 alpha minus half into alpha squared plus alpha squared plus alpha squared plus alpha square. So thus the objective or the Lagrangian objective that you're trying to maximize is 2 alpha minus half into 4 alpha square, or 2 alpha minus 2 alpha squared, which if you differentiate with respect to alpha set to 0, you will get alpha equal to half, right? Which means that alpha 1 equal to alpha 3 equal to half, alpha 2 equal to alpha 4 equal to half. And now we had already given the we can expression for w. So w is written as summation over n as alpha I yi xi. Since we can trivially write this in terms of only the support vectors, if you see, because all the non-support vectors will have alpha I is equal to 0. So in essence, all we need to do is to write for the support vector 1, which is half, alpha is half, y is half, xi is 1. For the other points, other two non-support vectors, we have alpha I is equal to 0, so we don't need to bother about them. The point number 3, for that we have alpha equal to half, yi equal to -1 and xi equal to -1. If you do the calculations, you will get w equal to 1, which in this case is just a scalar, right? So you have been able to calculate w now, and you need to now calculate b. So for finding b, you could have just trivially looked at any example, right? Let's pick up any support vector, because the support vector we know that yi times wx plus b minus 1 equal to 0, or yi times yi scalar into wx plus b equal to 1, and we can also multiply both these sides by yi, since we already know that yi squared equal to 1, because yi is either -1 or 1. So then you can write wx plus b equal to yi, or b equal to yi minus w dot xi, right? So let's try and solve this for the first example. We know that for the first support vector, we know that b is 1, yi is 1, w we already know is 1, and xi is also 1. So I'm talking about this example. yi is 1, xi is also 1, and w we have calculated to be 1. So b will turn out to be 0. If we do it for the other example also, yi is -1, w is 1, and xi is also -1. So if you do the calculation, you will again get b equal to 0. In practice, many implementations just average this out, this calculation over all the support vectors, just for some better precision or some better tolerance. So you just do b equal to 1 over number of support vectors, summation I equal to 1 to number of support vectors yi minus wxi. So basically over all the support vectors, you just average out yi minus wxi. For this particular case, we'll get b equal to 0 if you go through the total calculation. So thus we've been able to recover w equal to 1 and b equal to 0 even for this case, even in the dual formulation. Now this was really easy to solve in the dual formulation, given the inherent symmetry of the problem, and given that there was an easy geometric interpretation. In many cases that's not the case, and that's where you'll require a proper quadratic program solver. The final thing in today's lecture, how do we finally make predictions? You've learned a model. Learning a model essentially means learning w's and b's, and learning and in some sense maintaining the support vectors, right? So making a prediction is trivial. You just look at the sign of, for any test point xi, you just say y hat of xi is just the sign of wx plus b. So for this particular previous example, for x equal to 3, right, so we already know that w is 1 and b is 0. So w1 into 3 plus 0, and the sign of that is plus 1, right? So this will be predicted as plus 1 class. Point equal to some point as so test point xi equal to -3 will be predicted as sign of -3 plus 0, which is sign of -3, which is -1, right? So thus a blue point over here would be predicted to be -1 class. So that's making the prediction using the primal format or the primal formalism, but you could also do the same using the dual formulation. So y hat of x test is just the sign of w dot x test plus b, but you can replace w with summation I equal to 1 through all the support vectors alpha j yj xj dot x test plus b. And in the example that we've been using, we had alpha 1 equal to alpha 3 equal to half, alpha 2 and alpha 4 was 0. So thus y hat of 3 could be written as sign of alpha 1 into y1 into x1 into x test, so half into 1 into 1, so xj dot x test plus half into yj for the example, which was y equal to -1, or support vector with x equal to -1 and y equal to -1. So for that we had alpha equal to half times yj equal to minus half, and the dot product between -1 and 3, and this entire calculation comes out to be the sine of 6 over 2 or sine of 3, which is +1. So using both the primal and the dual formulation, we can make the same prediction. Okay, so with this I'll end today's lecture. In the next lecture I'll be discussing about what to do if the data is not linearly separable as it is. So that's where a lot of the power of SVM comes into play. Thank you.